This is section 4.4, the second derivatives and concavity. In this video, in this session, we will try to answer the question, what does second derivative say about a function? Okay, that means this is the main question, how the second derivative is related to the function, what information we can get. Let's look at these two figures. We have two graphs, function f and function g. Both of them are increasing. We can easily say they are increasing, but they have a little bit different shape. They look different because they are bended in different direction. Okay? And we have to know how to distinguish the difference, how to figure out if the function is bended upwards or bended downwards. Before we start, let's use a little bit more professional terminology than bended, because we do have different terminology. And let's look at this. Yeah. This is the same function. Please ignore the tangent lines at the moment. At this point, we will look at the tangent lines in a minute. But what I would like to say that bended up in mathematics, we call concave up, concave upwards. Okay? Concave upwards, bended down, we will call concave downwards. And this is the short definition and one of the definition, like how to recognize when we see the graph, how to recognize if the function is bended up or down. We may notice actually now, let's look at the tangent lines. When you have a curve and you will draw a tangent line, we know how to draw a tangent line will be placed below the curve. Or maybe, let's look from the curve perspective, curve will be above. If the curve is above its tangent line, then the curve is bended up, actually concave up. On the other side, if we draw a tangent line and the curve is placed below the tangent, as we can see, tangent line and the curve is below the tangent, then we will say the curve is bended down and actually concave down. Okay, that's one of the definitions. You may always, sometimes we're not sure because we may have the point that function is changing concavity, and you can always try to draw a tangent line and then you will see if the curve is above, then we have no question, like we will have no doubts to define concavity. Okay, but now let's look at closely. Let's determine where the function is concave up and concave down more explicitly. Okay, the same graph. Now let's look closer at these tangent lines. We can see, we know that is concave up because curve is above the tangent line. But let's think about the slope of the tangent, how the slope is behaving. The tangent line is not extremely steep, this one, and as x progresses towards infinity, we may notice that the tangent line is more steep and even steeper. Okay? Slope of the tangent line is getting bigger. So I can say the slope of the tangent lines are increasing. Okay, increases. Now, if we remember from the first derivative, if something, let's call it f, if f is increasing, then its derivative is positive. Right? Because we have to make sure that increasing and positive, they're a little bit different feature, different things. But if something is increasing, derivative of something is positive. Now we have slope of the tangent line increasing, then derivative of the slope is positive. Now, just not to be confused, slope of the tangent is defined like this. That's slope, f prime. Yes, we know that this is slope, derivative of the function, slope of the tangent. If f prime is increasing, then its derivative is positive. And then we reach the statement which includes the second derivative. Okay, so this is the conclusion. F prime is increasing, still the same. Okay? And since f prime is increasing, that's f prime, its derivative is positive. Okay, its derivative is positive. It means function is concave up, concave upwards if the second derivative is positive, because through the tangent, through the first derivative, we reach the second derivative, but we still have to relate to the original curve f. It means function is concave up if the second derivative is positive. Okay, that's the answer to the question on the top of the slide. And the same thing happens on this, on concave down, respectively the same. Analyzing the slope of the tangent, steep, a little bit less, even more less, and it's actually becoming almost horizontal. It means slope of the tangent lines, they are still positive, but slope of the tangents are decreasing. Slope of the tangent decrease. Okay, and then if function is decreasing, then its derivative is less than 0. Now, slope of the tangent is derivative. Slope of the tangent decreasing, then its derivative is negative, less than 0. Okay? If f prime is decreasing, this is f prime, its derivative is negative. This is the conclusion. Second derivative is negative for the function to be bended down, concave down. Okay, and that's the definition. Let f be a differentiable function on the open interval AB. Then function is concave up if the slope of the tangent line f prime is increasing, concave down if the slope of the tangent is decreasing. That's one statement. And then involving a second derivative, if the slope is decreasing, its derivative is positive. Then second derivative is positive, it's for all of the x's in the interval, then graph is concave up on that interval. If the second derivative of the original function is negative for all of the x's in the interval, then the graph is concave downwards on that interval. And we can nicely see. Okay, another thing we have to define before we start practicing more and applying this property more intensively, the point that function is changing concavity. And let's look at the graph. We can see this is the point, looks like function is concave down and then concave up. And again, some point, concave down. Oh, this is a little bit weird, concave up. This point is interesting. However, function is not changing concavity. Concave upwards and again concave upwards. Point P is the point that we change in concavity. The points where function is changing concavity are called inflection points. Okay? All of them are the inflection points. That's the moment that function, the curve, is changing the concavity. Now, how can we find out explicitly these points? Let's have a definition. Yeah? Inflection points, we have to, first of all, yes, we will solve this equation. Second derivative is 0, and we will get points if we have the solution. Or we have to also find out where the second derivative is undefined. Second derivative 0 and the second derivative undefined. Solution of these two conditions will give us a set of numbers which are potential candidates for the inflection points. Not all of them. Please remember, not all of them are the inflection points. Because then what we have to do, we have to check the sign of the second derivative at these points. Second derivative must change the sign. That means when we will have, we remember the first derivative test. This is not exactly second derivative. No, we do have it. Let's say we have C1, 2, 3, and we testing the sign of the second derivative. And we can say this is second derivative is positive on that interval, negative, negative, positive. So we know that function is concave up if the second derivative is positive, concave down, concave down, concave up. And now, changing from positive to negative, we will have inflection point. But being concave down and again concave down, no, that's not an inflection point. Concave down and concave up, yes, this will be the inflection point. In general, function the second derivative must change the sign at these points. Then we will call that, yes, this is the inflection point. Yes, we can nicely see here. Okay, inflection point. Okay. And yeah, I have the graph, but let's just do one exercise and later we will have more practice session. Okay, find the points of inflection and the intervals on which this function is concave up and concave down. Okay, we have nice and easy function because this is polynomial, the fifth degree polynomial. Polynomials are nice and smooth, defined everywhere. That's in domain, are all of the real numbers. We good with this. Okay, for the inflection points, we know for the concavity, second derivative is involved. So let's find the first derivative, 15x to the power of 4, 20x to the power of 3 plus 0. And now one more, 60x cubed minus 60x squared. Okay, second derivative is defined everywhere. That means we will only try to solve this equation. Second derivative equals to 0 if 60x cubed minus 60x squared equals to 0. We can factor out 60x squared, x minus 1 equals to 0. And then 0 product property. For this product, 60x squared must be 0 or x minus 1 must be 0. This is 0 if x is 0 and x equals to 1. Okay, that's we do have two potential candidates. Please do not list them right away as inflection points, because what I will do now, I will place them on the number line and I can take different color and I will test the sign of the second derivative. Maybe that form is good. Always the factored form is good. It's the same like this one, but let's see. Okay, when I take the test value, for instance, negative 1, actually x squared, any quantity squared will be always positive. That means this is always positive. Negative 1 minus 1 is negative. Okay, let's take 1/2. Again, 60x 1/2 squared will be positive. 1/2 minus 1, it's still negative. And let's take 2. 2 minus 1 is 1 positive, and square will be positive. Okay, then blue function. When the second derivative is negative, function is concave down. Concave down, concave up. It means only at one function is changing concavity. And this is, I have the graph of this function. We can nicely see function is concave down. And it is something happens. Yeah? Probably we have a horizontal tangent. And that because of the degree of the polynomial, the function is flat here, but it's still, again, concave down. Yeah, we can see concave down. And at one is actually changing concavity. Don't worry, we don't have to graph for this question. We don't have to graph. We just have to find out the intervals. It means for the function to be concave up, x belongs to, and we can combine from negative infinity to 1. For function to, down. Function is concave down. We can see. And then concave up for all of the x's from 1 to infinity. And 1, of course, x equals to 1. Only that point, because we're changing the sign, is the, let's say by p, inflection point. Okay, that's the way to find intervals of concavity and inflection point. Okay, I will finish this session, but please definitely check the practice problems, more application of the concavity and inflection point. Okay, thank you.